query optimizer. So when you submit the query, the SQL, like the select the first name, last name from the employee, and department where the department name is the HR, something like that, then that query will be processed, okay, to access the data. The first thing is the parsing, scanning, and the validation. That means first your query should be correct in terms of syntax, right? So it will check the lexical analysis as well as, so even though your query is perfect, you should have the permission. Or also, there should be the table that you specify, right? Even though your query is correct in terms of syntax, the data, like the table name, column name, and or the something data should be correct. So that should be validated. Also, you should have the proper permission to access the data. Then, if everything is okay, it will be converted into the parsed form, which is called the parse. Parsed form is then it's ready to access the data. One more thing. There is one more thing should be done before you access the data is the query optimizer will find the best way to access the data. As we have seen the last class, there are a bunch of different ways to access the data. Among them, the query optimizer select only one, just one path to access the data. That is called the execution plan. So, query optimizer will make the plan, like the trap, your plan of the travel. Okay. So first you visit New York, then Boston, then so on. Then how you can move there, like I'm going to take a walk, I'm going to take the train, I'm going to take the airplane, something like that. You will make the travel plan when you have the travel, just like the query optimizer will make the execution plan. At that time, how query optimizer decide the best plan? There are two ways. One is the cost-based. Another one is the rule-based. First, the rule-based is you have the certain rules. For example, first rule is using primary key. If there exists, if your query use the primary key, we will use the primary key. Then secondary key. Then clustering key. Then finally, the last option is brute force way, full table scan, right? Full table scan is the lowest approach. It's not actually the slow approach, but the table scan is the last rule. So you can apply the rule by rule. On the other hand, the cost-based optimizer compute the cost for each case, each and every case. For example, when you have the 12,000 different approaches to access the data, you will compute the cost. Just like when you compute the price, the cost of your travel. So when I take the plane, it will cost the 10,000 bucks. Why? When I take the train, it will cost the 1,000. So I will take the 1,000, the travel plan. It's the exactly same thing. So we will compute, the optimizer will compute all the cost of the approach, then select the lowest minimum cost as the best plan. That is the cost-based optimizer. So today we will see how we can compute the cost. Okay. Then before we start, by the way, how we can compute, how we can consider the cost when we access the data. Somebody may easily imagine time, right? Yes, it's definitely time. But in terms of the computer architecture, we can consider something.
Distance.
User time, sys time, idle time. There are a bunch of different time, but we are familiar with the wall clock time, just the stopwatch. Then measure how long it takes to execute the run. But it's not stable, depending on the various situations. So wall clock usually not used. So how can we measure such a cost?
Using resources.
So for example, we can consider some overhead like the storage cost, computation cost, also the memory cost, and something, all other costs. Among them, we will take only secondary storage cost, which means seek time and access time. Why don't you go back to your knowledge of the operating system? I think right now it's time to learn the file system, right? At that time, you learned how to access, how to find the data. There are two types of costs, the seek time and access time. Seek time is you realize where the file is, the block is located, and the search time is moving forward and backward of your disk content. Finally, you got the data, something like that. However, that cost is the most expensive cost comparing to the other is everything. So we will consider only such a secondary storage access cost. In other words, it's the number of input and output I/O. Input and output number. It's a block. So we will consider number of blocks that you need to access the data. When you access the data, how many blocks you need to access? When we learn about the indexing structure, we learn how we can access the data. First, when you have the B-tree structure like this, so this is a file structure, it's a block. So 1, 2, 3, finally 4 I/O are needed, something like that. Then, if we have this index, we can say this index is faster than the first one, right? Because it needs 1, 2, 3 I/O. However, this one is 4 I/O. So we can say this is faster than this. It's the same thing. When we compute the cost, we will calculate the number of I/Os when you access the data. Okay? So, there are two main costs when you when you execute the query SQL. That is selection. First, we need to access the data. We need to select the data. Another one is when you have the two tables, we need to consider join. Okay? So we will first take a look at how we can compute the cost to select the data from single table. The next one is the join cost. When we join the two tables, how much expensive? Okay? There is another one that is the join order. Okay? Join order. But join order can be considered in the join operation. So mainly we will take a look at the selection and join cost. First, the selectivity. Why don't you take a look at the handout? There are list of the selection method. As we discussed before, there are a bunch of different selection methods. The first one is a linear search. In other words, brute force search. Also, it can be called as the full table scan. We do not use any indexing structure. We just read, write, record by record, block by block. So it's a linear search. Second is a binary search when the data file, the table is sorted. If the table is already ordered by the key, then we can use the binary search. Everybody knows what is the binary search, right? So we can use a binary search. The third option is a primary index or hash key index. When we have the primary index is the index of the anchor key that we have learned before. Also, primary index for multiple record is different. When you access only one data, it's different from the multiple data. So sometimes S4 is called range query, range search. Okay. The next one is a clustering index using the clustering index. So clustering index is for, think about the example. What is the example of the clustering index? D number, department. Okay, if you can make the index for D annual, it's an index of simply 1, 2, 3, 4, 5. The difference between clustering index and the primary and secondary index is for each key there are many records. It's a group. So it's called the clustering index. The next one is a secondary index, which is the most popular one, using B+3 index. Conjunctive selection is the combination of the previous one. So we will take a look at the cost of each selection. First one, linear search, or brute force, or full table scan. Before that, we try to define some variable. First, n is the number of record, the number of data, okay, for each table. N is the number of a table, and BFR is a buffering factor. Can you remember what is a buffering factor? How many records in one block? Why? Why do we need the buffering factor? Each block is a unit of I/O. So when we compute the cost, we are not going to calculate the number of records. Instead, we will calculate number of blocks. So that is the reason buffering factor is more important. X is number of levels of index. For example, in this case, if you have such a B3 index, how many levels? 1, 2, 3. So X is the level of index. Then next, capital letter R is record size. If you have the fixed length, you can just sum up. Otherwise, you can average, or you can sampling real data. So this is a record size, usually average. Next, BI1 is the number of blocks for this leaf node, first level index node. Sometimes we can use sibling node to access the data, right? We don't have to up and down. Instead, when you search the range query, we can utilize the sibling node. So at the time we need the number of blocks in this, the first level index. The next, D is the distinct value. How many distinct values? For example, what is the distinct value of D for primary key? How many different values of the primary key? Only one? Primary key is all different, right? It's a unit. So that is the same as number of records, right? So, what about the DNO? We have two departments. How many distinct values of DNO? Two. Okay, even though you have the 20 employees, okay, the D distinct value of DNO is 2. So this is the D distinct value. Then selectivity is the fraction of the data. So for example, we have DNO 1, DNO 2, DNO 3. So we have a total 3 distinct values of the DNO in employee table. Okay? There are total 20 employees. So N is 20. At that time, we have 5, 10. Okay? 5 of the DNO number 1. 5 employees in DNO 2. 10 of employees DNO 3. At that time, the selectivity. Selectivity is the 25%. DNO1 has the 25% of the selectivity. It's a fraction of the data, percentile of the data. Okay? What about this one? 25%? It's a 15%. Why the selectivity is important? If the selectivity is high, for example, it's a 2 and 18. So we have this is 10% of the selectivity. DNO equal 1 has a 10% selectivity. DNO2 is 90% of selectivity. Okay, at that time, even though you have index of the DNO, you don't have to use index. Instead, full table scan, linear search is faster. Why? Because you have 90% of the selectivity. Anyway, you need to read 90% of the data for DNO equal to 2. Okay? Do you understand what I'm saying? If you use the index, when you search the DNO equal to 2, for example, select first name from employee where DNO equal to. Everybody believes indexing is the fastest way. So Professor Lee said, using index we can access the data very fast. So you use the DNO index. However, in this case, it's much slower than linear search, full table scan. Why? You need to anyway access index. Index, then 5. Index, index 5. Index, index 5. All 90% of the data. Instead, why don't we use full table scan only for this? Even though we have the 10% of the DNO1, that can be ignored. So this is the idea of the selectivity. Okay, we need to consider such a selectivity in case of what? Range query. What is a range query, by the way? Using inequality. Like this one. Or like the clustering index. Okay, that is the selectivity. Then, selection cardinality is the same idea as the selectivity. Selection cardinality is the selectivity times R, number of the data. Where's the number of record? It's R actually. N or R. So it's a number of data. 15% times 20 data. It's a 10. Okay? It's called the cardinality. It's a number of data for each. Okay? So this is the most of the thing variable. Then let's start from the linear search. Linear search. That's that. So for linear search, how can we compute the cost? Cost should be represented by the number of blocks. How many blocks do you need to access? So in this case, we have, there's one more thing, is the B. B is the number of blocks. The most important thing. Okay, forgot that. So B, number of blocks. So how many blocks do you need? So this is an employee. Employee has total B number of blocks. How many blocks do you need to access the data of the employee using linear search? It's a, if you are lucky, it can be 1, right?
Yes.
You can find the data from, so let's say this is the block of the employee. How many? B number of blocks, right? Then, if your data is here, 1. However, sometimes it can be n, last one. So, average B over 2. So, if when the query optimizer compute the cost, in case of linear search, it's a B over 2. To solve that problem, you should know number of blocks. Okay? The next, binary search. Binary search is a cut in a half, compare, then cut in a half, and cut in a half. In case data are what? When you can use the binary search? When you can use binary search rather than linear search.
The data is also
Data is sorted. If the data is sorted like the textbook, why don't you find the page 100? If you don't want very complicated stuff, you can over until the 100. But if you are smart, you will check cut in a half. Then this is a 5, 5, 9. Then half and half. Okay, this is much faster than from the beginning. So if you turn over from the beginning, that is a linear search. If you cut in a half, that is a binary search. How many blocks do you need to access the binary search? It's a log B based on 2, right? So this is the complexity. Then we have another overhang like this. What is this? If the query, for example, select first name from employee where SSN equal 1, for example, this is the unique. It's a primary key. So you will access only one data, right? In that case, it will be like this, log B based on 2. However, if you are accessing the data like the SSN is bigger than 10 and SSN is less than 20, like the range query. Okay? At that time, you need to, if SSN is not a good example, DNO is 1. If the data is not the unique data, only one, it's not 1, it's a range. Okay? So the data is already sorted, right? So you can cut in a half. Then finally you got the block where the data is located, 1. You need to access all these data, right? So you need to compute the number of blocks of this range. Okay? That is, what is the S? S is the selection cardinality of the data. For example, cardinality of DNO is equal to 1. Divide by buffering factor. Which means how many blocks for 1, right? How many blocks for 1? Then minus 1. Why minus 1? Because we already compute the first block. Okay? So we already consider the first block, so it will be minus 1. So in case this is a unique data, this will be 1, so this will be 1 over something. Okay? So for example, buffering factor is a 5. So this will be 1, so this will be log B over 2 in case of unique. In general, to compute this. Okay? The third one. So primary index. So what is a primary index? It has the data file. Then this is a data file. We have the index of this, right? It's for the primary key. So we have the index file. This is not a B plus 3. Before B plus 3, we have learned about primary index. Primary index can be dense index, non-dense index. Okay? In case the data file is already sorted by the primary key, it will be non-dense index. We can take only the anchor. Otherwise, we need to have the older pointer, that is the non-dense index. In this case, how many IO do you need? 1, 2, 3, plus 1. 1, 2, 3, plus 1. Always 1, 2, 3, plus 1. Number of level plus 1. So we need x plus 1 IU. Okay? We have another type of primary index, that is the hash index. I didn't explain the details about the hash index, but basically hash index use the hash bucket, right? So usually we can say we need 1 IU. Actually, that is the approximation. In real system, it's various, but it's very hard to measure the hash index, the cost, so we can say just 1 for hash. So don't pay attention too much to this value right now. S4. So primary index with range query. So multiple record. So multiple record. I deleted this one once again. Block ID, right? So level 1, 2, 3, and this is the 5. In case of the primary index unique record, we can access only 1 times of the IO for the 5. What if the range? Range is like this much. What is the example? So SSN is bigger than 1, for example. First, you need to find where 1 is located. How many IO? 1, 2, 3, 4. Then you need to search all of this bigger than 1. So we don't know how many blocks we need to access. So we can give the average, x plus b over 2. This is the average number of blocks of the data file. Okay? As you can see, actually, which one is faster?
Linear.
Linear search is faster. That's true. So even though, for example, somebody tests for this one, I create the social security number as a primary key, so we have the index for the social security number. So I learned that this one. You cannot figure out which one is faster when you have the smaller data. But what if you have the 1 million of data? Then you will realize linear search is faster. Your query is slow. It's not because your index is wrong, but because of this one. You need to access this, then linear search. Yes?
What in case if you have sorted data? So this will be faster, I think.
Sort data, but you don't know how many blocks you need to access. Like this one.
Yeah,
this is the bigger than 1, so you need to actually access all the blocks, right?
Yeah, but we firstly will access to the
yeah, that is the reason it's the average, right?
Okay.
It's average. If you are lucky, it will be the last one. So it's 1 block. If you are not lucky, this one, you need to access all the blocks. In addition to levels of index. Okay?
Yeah.
So index is not always the best solution. That's one of the common mistakes. Okay, index is not always because of the such a thing. Next, clustering index. Clustering index is like this. We have like the block pointer, like this one. So, clustering index, because first we need to access the level of index x plus. We need to access range. Okay, that is based on the, I think the same as this one. How many blocks is the selection cardinality? For example, dn is equal to 1. So we need to access the index x level of index x number of IOs. Then we need to access all the block that belongs to this one, right? That is based on the selection cardinality. For example, in previous example, this is 2, 0, 1, 2. 2 is a 50%, and times 20 total data is will be 10. So 10 over blocking factor, that will be number of blocks. Okay? So this is like this. The next, D plus 3 index. The secondary, generally we can say that set the secondary index, but it can be used for the primary key and secondary key and the candidate key also. So this is the same as D plus 3 index. First, we need to access the level of index x. Level of index, so x plus, actually, if that is unique, only 1, right? Plus 1. However, we can use the range query for b plus 3 index, just like this one. Okay? So, to general, we can have the general, that is x plus s. Why x plus s?
Because it's maybe a block of...
So, for example, we have SSN equal to 1. And SSN equal to 1. In this case, how many IO? 1, 2, 3, 4. 3 plus 1. So 3 plus 1. What if this is bigger than 1? What if dn is equal to 1? Using b plus 3 index. So we can access 1, 2, 3, right? 4. Then 1 belongs to the sibling node. So we can have the same number of the 1. Selection cardinality 10 times, or it was 25% times 20, that will be 5. So 5 times we need to access. So that is x plus s. Okay? What about inequality condition? In equality condition, we need to access the sibling node. So x plus how many times? Let the number of this one, half. Okay? Which means ei1 divided by 2. That is this number of first level index. We don't know how many we need to read. So guess as the half. So number of first level block, half of them. Plus, we need to access the data file. How many? We don't know. So half. So this is like this. This doesn't have to be full ceiling, just the parenthesis. Okay? Any questions so far? Not easy. Why don't you try to understand? It's not the rocket science to understand. It's not that difficult. But if you do not carefully read the textbook is more difficult to understand. So I try to summarize all the course function as one table. Why don't you make the case, simple case. For example, I have the employee table with 20 record, and it has 3 levels of the index and so on. And buffering factor is 5, and the record size is 100 bytes, and the block size is 500, something like that. Then compute the case. Then you will realize such a thing. Okay? So then, what about the conjunctive selection? Conjunctive is a combination of the operation, like the multiple selection condition, multiple join condition, multiple. At that time, you can compute for each, then select the minimum. Okay? For example, DN1 is equal to 1 and SSN is equal to 10. At that time, first you need to compute for each, then select the minimum. So conjunctive selection is one of the previous one. Okay, the next page. There are some examples. So this one. So we have the employee table. It has a record. The number of record is 10,000, and block, number of block is 2,000, and definitely blocking factor is 5, right? Okay, because we have the 5 blocks, so each, we have how many blocks? 2,000 blocks, right? 2,000 blocks, yes. Yeah, so each block has 5 records, so total 10,000 record employees in this. Then, what about using clustering index on salary? For example, we have the select the first name, last name from employee, where salary is equal to 10,000. Suppose that we have such a query. We'd like to compute the cost of this query using, in case when we use the clustering index on salary. Okay? So, clustering index is this one. Right? So, X plus S occurring factor S. Okay? In this case, we will say that this is a level of index. X is 3, and salary is more information. These two, before we compute the cost function later, this is more information about the employee. Okay? So we will compute the cost. For example, we have the clustering index on salary. That salary has, that index has the 3 levels. Okay? And cardinality of the salary is equal to 20. I'm not sure whether there is a $20 salary. But anyway, 20 for the salary $20. It has the 20 cardinality. Okay, what does that mean, cardinality? For each salary, in this case it's not the number of salary. The average cardinality is 20, which means for each salary, for example, 10K, how many employees? 20. 20K, average 20. Okay? The best way is for each value, we'd better have the data, cardinality. However, how many different salaries? It's too many. So average, roughly average cardinality is 20. So for each value, average 20 employees belongs to that salary. That is the average cardinality, okay? And second, we have another index for SSN. It's a secondary index. The level is for cardinality of the social security number is 20. It's the same thing. Okay? So for each social security number, there are 20. And so on. Then, eventually, third page, we can make such a table, lookup table to compute the cost. Okay? For example, table info, we have the employee department. So, employee has a 10,000, blocking factor is a 5, number of block is the 2,000. Department, we have 125 department, blocking factor is 10, which means it's the smaller size of record. And number of block is 13. Then index info. We have total 4 indexes for employee, 2 indexes for department. The salary is a clustering index. The social security number, DNO, sex, and sex are the 2 secondary index. Okay? For each index, we have the information about the level and cardinality and the number of blocks for the first level and distinct value, and so on. We have another thing, join operation. We will take a look at details example later. So join. This is a selection. This is a join. How join is a process? We have 2 tables like the R and S. For each record, we write compare the data. This is the brute force, the Cartesian product. In case of Cartesian product, we need R times S. Actually, it should be smaller letter, lower letter, right? So this is a table R, this is a table S. Number of record in table R, number of record in table S. How many total operation? R times S. Okay, this is a Cartesian product. So first, nested loop join. What is a nested loop join? Nested loop join is the first we access the first one, inner table, then access the outer table. So, first we need to access the left-hand side. R, S. Number of block. We need to access the number of block, left-hand side, table R. So this block, number of block for table R. Okay? Then plus, how many times operation? R times S operation. R times of S, I are needed. Right? Whenever you need to compare with the joint condition, you need to access the data. So BR times BS. Then, if that is matched, you need to save, right? For example, select first name, last name, where are from, employed, department, where manager, social security number is equal to SSN. This is the join operation to list up the name of manager of all department, right? At the time, first we need to access the employee, then find the department. If this condition is satisfied, we need to save, right? That is IO, input and output. Okay, so that will be calculated as this is a join selectivity. How many data are satisfied in this case? Okay? It's a how many? It's a percentage of the, for example, it has 100. It has 10. Okay? 10 of them are matched. Right? How many manager? 10 manager. So it's a 10% of the data are matched with the join condition. So this will be 10% times this one times this one. Then we will have the number of the IO divided by the buffering factor. So this is always the same as the any kind of join operation. Okay? So this is the nested loop join. Next one is a single loop. Single loop means we are going to access index to access the right hand side table. Okay? So this is the same. First we need to access the number of blocks in the left hand side. Then right hand side, not just S, instead we can use the index X plus, this is the same as X plus S, this one, secondary index. Then plus this join for the data satisfied with the join condition. Okay? The clustering index, why don't you take a look at this one? In case of clustering index, we need to consider the cardinality of the data. So that will be represented in the S divided by buffering factor. The others are same. Primary index, in case of primary index, this will be just 1 because it's a unique. We don't have to access for each data. Then hash, you don't have to worry about the hash in this case. Okay? We need to define another one, so it's more complicated. Don't worry about the hash. So this is the most popular one, nested loop join, single loop join. Another one is sort merge join. Sort merge join is a little bit different because we need to sort for each table, then join from the matched one. So we should know the cost of the sorting. That can be represented by the CS. Okay? So depending on types of the sorting algorithm, it can be various. Okay? Then after sorting, how can you access the data? Because they are sorted by the join condition. So you can start from the beginning. You can start from the beginning. If they are matched, yes. Otherwise, moving next. So how many total IO? R. How many total IO? Yes. S. So that is the CS. CS is the costing of the sort costing. Then BR plus BS. Then join part. That is the sort and merge. Okay? So we have learned about the cost of the selection. We have learned about the cost of the join. Then next one is the example. So this is the same as the previous example. Employee table, we have 10,000 record. And number of block is 2,000. And buffering factor, so 5. And number of department is 125. And block is 13. Okay, then. Primary index of the department. The other informations are in this table. Okay, you can utilize the information about this. Later, I will explain how real DBMS used this one. Okay, also we have the exercise lab. At that time, we will see real example of the Oracle, how Oracle generate this kind of information. Anyway, so let's take a look at this. So the number, if you can see the table of the index underbar info, the department has the primary key as with the DNO, Okay, what is the level? It's a 1 level. Okay, and the secondary index is a manager social security number. Level is 2 and cardinality is 1, which means 1 for each. Then so we have the employee. I think we have the more example in the slide. Let's take a look at this one first. Let's see this one first, then move to that one. Any questions so far?